Welcome all to the 9th lecture in the lecture series on circuit and system. I am Nikhil Kumar Nigam from EEE Department, Delhi Technical Campus. We will proceed further with having a recap of what we have discussed so far in the last lecture, and then we will move on to today's objective. In today's lecture, we will have a look at what different type of systems in contrast or in reference to the circuit analysis. But before that, let us have a recap of what we discussed in the last lecture. In the last lecture, we discussed the mathematical operations using singularity signals. Basically, we used step signal, gate signal and impulse signal. We discussed that if we multiply any signal ranging between -infinity to infinity, and if we multiply it with the unit step signal ut, then the resultant signal will be confined between 0 to infinity only. Its past values will become 0. Similarly, if we multiply any signal ranging from -infinity to infinity with the gate signal, then this will be confining the signal into a time limited signal, into a time limited signal. And similarly, if we multiply any signal ranging from -infinity to infinity, and if we multiply that signal with impulse signal, then the resultant would be a new impulse signal. The only thing that changes is the area under the impulse signal. Now the area of the new resultant impulse will be equal to the magnitude of the signal at t equal to 0. So this is what we discussed in the last lecture, and on the basis of it we discussed some numerical problems also. Let us proceed further. So in today's lecture we will discuss about the systems. What are systems? I'll try to explain what are systems. Then we will discuss some basic terminologies to better understand the classification of system. So signals, so the system generally classified in static and dynamic systems, and we will have a look on numerical problems. Using this numerical problem, we will get the in-depth knowledge of static and dynamic system. Similarly, we will discuss what are causal and non-causal systems, and same will perform some numerical problems to have in-depth knowledge on causal and non-causal systems. Then we have time variant and invariant systems, linear and non-linear systems, stable and unstable systems. The systems are still can further be classified, but as per the scope of the syllabus of circuit and system, we will stick our classification to only these 10 kind of systems. Let us proceed further. If I ask you to define what is a system, then obviously something will come into your mind where you will see that system is a combination of physical components which performs a specific task. In normal day-to-day life, you may use this word system along with the words like music system, or the cooling system, or temperature control system, so why are we calling them as systems? Why a system whose output is music, we are calling it to be a music system? Whose output is cooling a room, then why are we calling it to be a cooling system? We must understand the word system first, and then we'll get to know why are we calling anything to be a system. So let me give a wording of a word definition for this word system. It is a physical arrangement of components to produce a desired output, So suppose we have certain components, and if they are arranged in a proper manner, then this arrangement, if it is producing a desired output on the excitation of exciting it with a particular signal, then that particular arrangement can be termed as a system. So there is a bit of correction. I would like to write a systematic arrangement. Now let us see why we call a system to be a music system. Let us see this example. Say we have a mic. This is our mic, and this mic is certainly given some voice signal. This mic is given certain voice signal. Then this voice signal travels through some wires into a amplifier, and the output of this amplifier is then fed into the speakers. Now the speakers can further be an arrangement of big speakers and small speakers. So we have these arrangement, big speakers and small speakers, where the voice is being amplified by this amplifier, and then in the output it is separately fed to these three speakers, where this speaker will be producing treble sounds, and this may be producing the bass sound, the bass in the sound. So what is happening here? We have designed a systematic arrangement of some components like mic, amplifier and speakers to give us the best signal at the output. So this was the definition, that it is a systematic physical arrangement of a components to produce desired output. So whenever there is a systematic arrangement of physical components, we call everything to be a system. Let us discuss one more example. Say we generally use power system. Power system is the systematic arrangement of generating station, where the electricity is generated, then this being directly connected to transmission lines, where this generated electrical energy is transmitted using these transmission lines to the distant places, and at the distant locations we have distribution system, which then distributes the electrical energy into different localities, say locality 1, locality 2, locality 3 and locality 4. Now this arrangement is termed as power system. Now just imagine that if I replace or if I shuffle these components, instead of having generating station here, can I have a distribution block here? And instead of this distribution, can I have a generating block here? Obviously not. The interchanging these blocks will not work, because these are designed, or these are ordered in a way to perform an appropriate task or the desired task, and the desired task can only be performed when at the first step we have the generating station, followed by the transmission lines, and following the distribution system. So the arrangement should be systematic. So why I emphasize that it should be a systematic physical arrangement of components to produce the desired output. So this arrangement is basically a system. This whole is basically a system. I can represent the whole system with a single block. Now this block is a system. It is getting certain input or excitation, and on the basis of this excitation it is producing certain desired output. So this is the representation of a system. So in the representation of a system, we represent a system with a block who is getting certain input, and on the basis of this input it processes the input and produces certain output. The system can be represented in the time domain or frequency domain. Depending on the way with which we are representing our signals. Say I am representing the input signal as xt, that is there is a variable x which is variable of time. Then if it is a input signal and I am getting the output as yt, where this y is the output variable which is also dependent on time. Now this system processes this input and produces this output yt. So this is the representation of a system. A system can be represented mathematically in the time domain as well as in frequency domain. Say the system is represented by this yt. Yt is equal to, say, 3 times of xt. That is, we have a system and which is represented by this equation, which says that the system will produce output. This is the output. The system will produce output by increasing or by scaling the input signal 3 times. That is, this system will get the output, get the input as xt, and it will scale that input signal. Whatever the input signal is coming, it will multiply that signal with 3 and it will send it to the output. So this way we can represent system using some mathematical equations. Now that means a system relates output and input by certain relation. Now depending upon how a system is modulating or changing the input signal to the output, the system can be classified into the various forms. Let us see the classifications. But before the classifications, I should discuss some terminologies which would help us in understanding the classification of the systems. Let us discuss the reference instant. First term we have is reference instant. Reference instant is the time instant at which we are considering the system. Say if I am making some changes into the system at t equal to 0, then t equal to 0 will become our reference instant. Say if at t equal to 1 I will change the system, I will bring some changes into the system, then t equal to 1 will become my reference instant, and this will be the reference instant in future if I consider this to be the reference instant. Similarly, I may have a reference instant at t equal to -1. That is, I bring some changes into the past at t equal to 1, t equal to -1. So we can have reference instant at any instant of time. So reference instant is the one at which we are doing our analysis, or we are bringing certain kind of changes into the system. So if I consider, let us discuss, say for an instant I am considering that I am bringing some kind of change or dynamics into the system at t equal to 0. That is, t equal to 0 is my reference instant. If t equal to 0 is my reference instant, then what will be t equal to 1? In reference to it, what will be t equal to 1? T equal to 1 will be the future instant. Future instant. And similarly, t equal to minus 1 will be the past instant. Past instant. And let us say for another case, this is our first case. Say for another case, t equal to 1 is our reference input, reference instant. Say t equal to 1 is our reference instant. That means t equal to 0 or t equal to minus 1 will be the past instance, and t equal to 2 and 2, 3, 4 and up to infinity will be the future instance. Future instance. So depending upon the reference instant, we can classify any time instant to be as our future instant or as past instant. So this will be required while understanding the classification of the system. Say this equation yt is representing a certain system. Yt is equal to xt. Yt equal to xt. Then we have to see that output, yt is the output, xt is the input. Then in the system we will see how the is depending on the input. Say t equal to 0 is our reference instant. Then at t equal to 0, what will be the input? Say input will be x of 0, that is substituting t equal to 0, and with this equation I can get the reference the output as well. The output will be y equal to 0. Now this says that output at t equal to 0 is dependent on input at t equal to 0. Similarly, if I change the reference instant from t equal to 0 to t equal to 1, then the reference instant will be input incident will be x equal to 1, x at 1, and the output will be y1. Now this y1 says, and this should be equal. Now this y1 says that output of the system at the instant 1 is dependent on the input of the input to the system at t equal to 1. So we can say that the present output of the system is dependent on the present input of the system. Let us see another example to have a better understanding of this. In the second example, we have yt to be equal to x of t plus 1. We will see how the output is depending on input. Let us consider the reference instant to be t equal to 0. So at reference instant t equal to 0, output is y0, and this will be equal to x of 0 plus 1, and this will be x1. Now this equation says that output at the instant t equal to 0 is equal to input at the instant t equal to 1. It means this, the present input or present output of the system will depend upon future input. Present output will depend upon future input. So this equation is stating about a system whose present output will depend upon the future input. Let us consider another example where yt is equal to x of t minus 1. When yt is equal to x of t minus 1, let us consider the time instant at t equal to 0. Then at t equal to 0, this equation will become y of 0 will be equal to x of minus 1. This shows that output at t equal to 0 will depend upon the input at x equal to t equal to minus 1. So that means the present output is dependent on the past input. So we have considered three examples here. In this example we saw that present output is equal to the present input, or present output is dependent on present input. In this example we saw that present output is dependent on future input, and in this particular example we saw that present output is dependent on past input. So these are three different systems. Let us now check yt. We have another system yt equal to 2 times of xt. This is our system. Let us see what this system tells us about. At t equal to 0, this equation will be y of 0 equal to 2 times of x of 0, and at t equal to 1, y of 1 will be equal to 2 times of x of 1, and similarly t equal to minus 1, y of minus 1 equal to 2 times of x of minus 1. What these all three equations saying? This is saying that output at t equal to 0 is dependent on input at t equal to 0. This equation is saying that output at t equal to 1 is dependent on input at t equal to 1, and this equation says that output at t equal to minus 1 is dependent on input at t equal to minus 1. That means if we have considered the reference incident to be t equal to 1, then the present input is depending upon present output. Similarly, when we consider the reference instant to be t equal to 1, then the present input again is dependent upon present input. And when we consider the reference input at t equal to minus 1, then present output will be again depending upon present input. Hence, this equation is saying that present output is dependent on present input. Now, let us see the next numerical, which is yt equal to x of 2t. Now, what this system is saying, at t equal to 0, we have y of 0 equal to x of 0. Now, this equation is saying that output at t equal to 0 is dependent on input at t equal to 0. But if I shift time further, let us say the reference instant now is t equal to 1. So y of 1 is equal to x of 2 times of 1, which is x of 2. This shows that output at t equal to 1 is dependent on input at t equal to 2. That is, the present output is dependent on future input. Similarly, if I substitute t equal to minus 1, then y at minus 1 is equal to x at minus 2. Now, this equation says the output at t equal to minus 1 is dependent on input at x equal to minus 2. It means this, the present output is dependent on past input, whereas earlier it was saying that present output was dependent on future input. Now it is saying that present output is dependent on past input. So this says that output may depend upon past, present and future values of the inputs. Let us consider the another example, which is y of t equal to 1 minus xt. So at t equal to 0, we have y of 0 to be equal to 1 minus x of 0. In this equation, we have this term 1, which is constant. That means it will not be varying with respect to time. So now the equation says that present output is dependent on present input. But if I change time, to t equal to 1, then this will be y at 1 will be equal to 1 minus x at 1. And similarly, if I change time to minus 1, then this will be y at minus 1 will be equal to 1 minus x at minus 1. So this is saying that present in output is dependent on present input. Again, the present output is dependent on present input. So this system is saying that the output will depend upon the present inputs only. This was also saying that output was will be depending on present inputs only, but this system is saying that output will depend upon present input, past input or future inputs. Let us consider one more example where system yt is equal to e raised to power t plus 1 into x of t. Now we have to comment whether the output depends upon input, past values of input, future values of input or the present values of input. Now at t equal to 0, the equation will be y at 0 will be equal to e raised to power 1, that is e times x of 1, x of 0. I have substituted t to be equal to 0. Now this equation says that output at t equal to 0 is equal to the or dependent on input at x equal to 0. So this t is not coming into any effect here. Similarly, if I change the time instant to 1, then y at 1 will be equal to e square times x of 1. Here the output at t equal to 1 is equal to e square times x of 1, that is the output at t equal to 1 will be dependent on output at x equal to x, input at t equal to 1, but it will be scaled. So over here this is acting like a constant, just like we discussed this. So the output will vary, but it will not depend upon the past values. In fact, it is depending only on the present values of the input signal. Similarly, let me change the time to t equal to minus 1, then y of minus 1 will be equal to e raised to power 0 x of minus 1, and this will be equal to x of minus 1. Now this equation is again stating that output at t equal to minus 1 is dependent on input at x equal to t equal to minus 1. That means the present output is equal to present input, or present output is dependent on present input. Over here also present output was dependent on present input, present output was dependent on present input. Though the magnitude is varying, but the dependence of output on the input is only on its present inputs, not on its past and future. So let us discuss this another example where y of t is equal to x of t plus 1 minus x of t minus 1. Let us comment on it. At t equal to 0, this equation will be y of 0 will be equal to x of 1 minus x of minus 1. This says the present input, present output will depend upon future input and past input. Similarly, if I change the time to t equal to 1, then the present output will depend upon x, it will be x of 2 and this will be x of 0. That is, in reference to this t equal to 1, this is future, this is past. So the present output is dependent on future input and past input. Similarly, if I consider the reference time to be t equal to minus 1, then y of minus 1 will be equal to x of 0 minus x of minus 2. Now this says that present output is equal to or dependent on the future input. See here, we are considering the time at t equal to minus 1. So in reference to this time, t equal to 1 is the future time. So present output is dependent on future input as well as on past inputs. So this system is saying that the output will depend upon future and past values. Let us consider another example where yt is equal to 2 times of xt minus x of t plus 1. Let us comment on it. Let us first check the output at t equal to 0. So output at t equal to 0 will be y0, that is, this will be the present output, and this will be equal to 2 times x of 0 minus x of 1, that is, the present output is dependent on present input and future input. Similarly, at t equal to 1, the present output will be y1, and this will be equal to 2 times of x1 minus x of 2, that is, the present output is now again dependent on present input and future input. Let us have another time instant t equal to minus 1. So y of minus 1, that is, the output at minus 1, will be equal to 2 times x of minus 1 minus x of 0. So if we are considering the reference instant at t equal to minus 1, then t equal to 0 will be future and t equal to minus 1 will be present. So this says that present output is dependent on present input and future input. So we will comment that this is representing a system where present output is dependent on present input and future input. Let us discuss one more. We have another very important, yt to be equal to x of t plus 1 and to the whole square. Let us first discuss it to be xt square. So at t equal to 0, y of 0, that is the present output, will be equal to x of 0 square. So it means the present output is dependent on the square of present input. Similarly, at t equal to 1, the present output will depend upon the square of present input. Similarly, at t equal to minus 1, present output will depend upon again the square of the present input. So this equation is saying that the output will always be depending on the present inputs only. Now what will be the change into the output or into the system if I add plus 1 here? Let us do so. Plus 1 here. Now at t equal to 0, if I substitute t equal to 0 in this equation, so the present output y of 0 will be equal to x of 1. Now this equation says that present output will depend upon future square of the future input. Similarly, at t equal to 1, the present output will depend upon the square of the future input, because if we are considering the time reference instant at t equal to 1, then at t equal to 2 will be the future input. So it means the present output will depend upon the future input square. Similarly, if I substitute t equal to -1, then the present output will again depend upon this will be 0. Now if the reference instant is at t equal to -1, so t equal to 1 will be the future, or t equal to 0 will be the future. So this means the present output again is depending upon future inputs. So this system will be saying that the output of the system will be depending upon the future values of the system. The knowledge of these dependencies is very much required in solving the numerical based on the classification of systems. We'll discuss very shortly. Let us have a last numerical. We have y of t plus 1 to be equal to x of t plus 1. Now we have these two inputs. We have a system whose characteristic equation or governing equation is this one. So at t equal to 0, the output y of 1 will be equal to x of 1. This says that the future output will depend upon future input. Similarly, at t equal to 1, y of 2 will be equal to x of 2. Now this says the future output will depend upon future input again. Or if I consider this to be the reference instant, then the present output is depending upon present input. Similarly, in this case, the present output is depending upon present input. And if I change the time instant to be -1, then this again will be y of 0 will be equal to x of 0. That is, at every instant the present output is dependent on present input. So this kind of system is saying that we have a system where present output is dependent on present input. So the conclusion that we can draw from the discussion on these systems is that whenever there is a time shifting in the input, or time scaling in the input, the system will depend upon past and present. For time scaling and time shifting in the input signal, the system will depend upon past and future inputs. Like there is no time scaling or no time shifting, so it will depend only on present inputs. Likewise, there is no time scaling, no time shifting, so it will depend only on the present inputs. But in this we have time shifting in this input and this in this input, so it will be depending upon present and past and future values. Similarly, we have time shifting here, so the system will be depending upon the future values. Similarly, we have time shifting here, we have time shifting here. So whenever the time shifting is there, we have a system which will be depending upon on the past and future values of the input. But in a case when the same amount of shifting is done in the time factor of the output, then the time shifting or time scaling will not affect. Let me give you one more example. Say y of 2t equal to x of 2t. Here the scaling is done in both the input and output. So it will not depend on the past or future, it will only depend upon the present values. Similarly, if we have t minus 1 here and x of t minus 1 here, then the same amount of shifting is done in the output as well as in the input. So this will only depend upon the present values, it will not depend upon the past and future values. So I guess that's it for today. In the next lecture we will discuss the classification of system. To classify system, the knowledge of the dependence of output on the input is very necessary. That output dependence on input is very necessary. So on the basis of the knowledge acquired in this lecture, in the next lecture we will classify system to be static and dynamic, causal and non-causal system, time variant and invariant system, linear and non-linear system, stable and unstable systems. So thank you so much for listening to the lecture. For any queries, you can mail me your queries at n.nigam@delhitechnicalcampus.ac.in, or you can WhatsApp me your queries on this number. I'll try to answer all your queries, or we can meet up into the tutorials to solve the queries.